Okay, so today we are going to be touching on two chapters. Okay, one is on the timer peripheral block, and the other one is on the UART. Okay, I actually uploaded one more additional set of slides for the ADC module. Okay, so that is for your own reading. It is not examinable. The reason why I took it out from the actual coverage is we don't. I mean, you have studied ADC before. You all know how it works, uh, and that more chapter is focused on how you can use ADC for the Freedom Boards controller that we have. We don't actually need to use it for any of the labs or the project unless you have some fancy idea. Okay. So that is why I took it out. Okay, you are free to go through it and learn on your own. Okay, but we're not going to be covering that. Okay, timer and UART are both important, all right, because these blocks are critical to the project. Okay, so that is why we need to make sure we cover this. Okay. Okay, so a few other matters first before we start. So the first thing is this two lectures. That means the one on the UART and then the PW timer module that we're going to go through. These are basically the last on the microcontroller hardware. Okay, so basically with this week we have covered all the important peripheral subsystems that we need. Okay, in order to make sure that we can control everything that is needed for the project. All right. Of course, the Cortex M0 Plus that you have is actually very powerful, and it has a lot of other features as well. Okay, but we don't have time to cover all of that in this module. But since you have the board, all right, so do explore it, all right, in your free time. Okay, once the semester is over and you have more free time. All right. So next week onwards, you'll be focusing on the OS part already. All right. OS part is in terms of actual slides and all, actually is lesser. It's more of understanding the concepts. As long as you understand the concept and you know how to apply it, then it's fairly easy. All right. Not as the content wise or material wise, not as heavy as the hardware and the controller hardware. Okay, so this is something I told you I will update you every week. This week and next week, the DSA lab is free, all right? Because both these weeks, it is online lessons for the EPP module, all right? Which means that if you want to come down to the DSA lab anytime and work on your project and or build up some hardware, you're free to do so, all right? So just take note of this. This week and next week is free. Okay, so let me have a quick sort of test or assessment of your last week material. Don't worry, it's not a formal assessment. It's just our usual quiz or poll that we have. Okay, can you all see the question? Okay, so this question is based on the IRQ config, okay, that we covered last week, and it's something that you would have done in the lab as well. All right. So look at the question carefully. One person answered very quickly. I don't know who is that, but okay, look at the question carefully and think before you answer. This is actually one of the MCQ questions from last semester's midterm paper. Okay, so what close to 90% have voted. So I'm going to end the polling now. Okay. So these are the results. Okay, and majority of you have chosen the last option here, which is hex 8000000. Okay, so let's look whether this is correct or not. All right. So we know that port D is mapped to IRQ31, which is over here. All right, and I'm going to set a priority of 1. 1 in binary is basically 0, 1, 0, 0. So, sorry, it's actually 0, 0, 1 in terms of 2 bits. All right. Why only take 2 bits? Because we only take 2 bits, and these 2 bits are mapped to the upper 2 bits of that 8-bit value. All right. So this upper 8-bit value here, basically what you will see, this first 8 bits here will be 0, 1, 0, 0, 0, 0, 0, 0, which is equivalent to 0x 0. All right, and since I say that no other interrupts are configured, the rest are all zeros. Okay, so the correct answer is D. Okay, so 26% got this correct. So the rest, I hope you understand now. Okay, when you are setting priority, it is only 2 bits, but the 2 bits are the upper 2 bits of each of the 8-bit block. Okay, so that is why the answer here is D over here. Okay, can? Okay, so those of you who got some other answer, I hope now you get a better idea. All right, so let me stop this. All right, and let's come back to our slides. Okay, so let's come back to our slides and we look at the material for today. Okay, so for today we are focusing on 2 things. The first half I'm going to be covering the timer block, and in the second half I'm going to be looking at the UART block. All right, and both of these are very, very important. Okay, I need to make sure you get them working on your board. All right, then only your project you can complete it. All right, so for the timer, we have a whole bunch of sort of timer subsystems within the KL25 controller. All right, so we have things like the periodic interrupt timer, the timer PWM module, we have a low power timer, we have a real time clock, and we have a SysTick as well. Okay, what we will be focusing on, I'll briefly touch on the periodic interrupt timer, and then we'll be focusing on the timer PWM module. All right, the rest of them are there. If you think you want to use them for the project or in the future, you're free to explore them. All right, but we'll be covering only these 2 modules in the lecture slides today. All right, so in general, what is a timer? Okay, a timer or a counter block. In most microcontrollers, timer and counters are sort of grouped together. Okay, and the whole idea is you have a preset binary counter which can increment, and this increment can happen periodically through a clock or through events. All right, so in some cases you can configure this counter to increment based on an internal clock, maybe with a prescaler. Okay, and in some cases you can tie this to an external pin. Okay, so if for example your EVP2, you did your encoder pulses and so on. So that is an example where you have external triggers, external pulses coming in, and you want to keep track of this count. All right, so timer and counter are usually grouped together as a single peripheral block. Okay, and some of these blocks you can configure them to generate interrupts. Okay, not all, but maybe some some may have this interrupt capability, some may not have. All right, in terms of direction, some of them can be configured to be up or down. All right, and you also may be able to detect overflow and underflow depending on whether you're counting up or counting down. All right, so these are general characteristics. Different microcontrollers may have some subset of these features. Okay, the more complex and more advanced the controller like what we have, you have more configurable options. If you go back to something like the Arduino Uno, you have lesser options and lesser sort of variations to how you can configure it. Okay, so we'll start off with this very basic application, which is the periodic interrupt timer. All right, so in this periodic interrupt timer, basically what you can do is you can load a start value, okay, to this register called load well, and once you load it, what will happen is the counter will start to decrement every clock pulse. Okay, so you have a clock that will count down this value. So this start value that I load, it will be buffered. Okay, and once the timer is started, all right, we will load this start value into the counter. And once it's in the counter, every clock that comes in, it will start to decrement. All right, and once the counter reaches 0, it can generate an interrupt, and it will automatically reload, okay, its original value and start over again. Okay, so it's a very simple counter. Okay, and what's the duration? Actual duration depends on the clock frequency you're going to operate on and whether you're going to use prescalers and so on. So there are other configurations that you need to look into. All right, but the general idea is you just put in a start value. Okay, and from that start value, as you can see, once it counts all the way down to 0, you will generate an interrupt and it automatically reload itself. Okay, so this is a very basic module you can use. All right, for example, if every 1 millisecond I want to trigger something, or every 100 millisecond I want to trigger something, so you do some calculation. Okay, for 100 millisecond, what is the value I should load into my uh, load value register, and then do the necessary configuration, start the timer, and then every millisecond this interrupt is triggered. All right, so this is one way of generating a periodic interrupt using this particular block. Okay, so this is just one of the basic blocks you can use. I will not go into any further details about this. You can refer back to the controller data sheet if you want to implement this. Okay, so what I'm going to be focusing on is the PWM module. Okay, why we need this is basically because you need the PWMs to drive your motors. All right, so in the project specification document that I've already released, I've given you, most of you have used the DRV chip, the motor driver chip from EPP2. Some of you may not have done EPP2 or have forgotten. Okay, so I put the link there as well. All right, so once this module is done, okay, and this week's lab is on PWM, all right, you can actually start to fix up your PWM driver chips and integrating them to your controller. All right, and then start to develop your code to control the motors. Okay, how you want to drive the motors depends on your own design. Okay, so you have 4 wheels. All right, and you have 2 motor driver chips. Okay, so now the thing is, most students in the past, basically what they do is they use one DRV chip for the left motors and one DRV chip for the right motors. Okay, that is one option. Okay, if you have some other idea that you want to use or you want to use for the back and front, up to you. Okay, there's one more thing that I will confirm later. Okay, there is also an additional budget. Okay, there's an additional budget for each group to buy things. Okay, the actual amount later I'll confirm with you after the break. So that additional amount is for you if you think you want to buy anything extra to add on to the robot. In the past, students have used it to replace the board that they completely burn and destroy. Okay, so that is one option. If your board survives, all right, and you don't need to buy a new board, then you can use that money to buy other things that can add some differentiation to your project. Okay, so the amount I'll tell you later. Okay, I'll just check back and confirm that before I tell you the amount. All right, so if you want to add more driver chips, okay, and you want to do 4-wheel control, also can. Last semester, I think there's one team that tried to do some fast and furious drifting and all. Partially succeeded, but of course bang all over the place. All right, so I'll leave it to you. Okay, so this is just an idea only. If you want to use the budget to buy more driver chips and do 4-wheel control individually, also is possible. Okay, but you need to look back at what are the PWMs available for you to use. Okay, so we will be looking at that later when we are going through the lab. Okay, so you need to be mindful that how many PWMs are available, how many of them are brought out to the pins, and how many you can use. Okay, so we will look at that in a while. Okay, so this is the general block of the PWM. All right, so in this you can see that this picture is a bit small, but next slide you'll see it a bit bigger. And important thing is you have, for each of these timer PWM modules, you have 6 channels. Okay, that means when I say I have this particular PWM module 1, okay, that module 1 has 6 individual channels. which can be configured separately. All right. So, and each of these channels, you can configure them to operate in different modes, either capture mode, output compare mode, or PWM mode. Okay, capture mode, output compare mode is used in a different type of scenarios. For example, capture mode is when I want to capture timer's value when input signal changes. All right, so let's say I want to know when an event happens, external event happens, so I can tie that to a pin, and when that signal is triggered, I capture the timer value. Okay, so I can know exactly when this event happened. So that is capture mode. Output compare mode is change the output signal when timer reaches a certain value. All right, so when my timer is counting and I hit a certain value, then I can change some output signal. Okay, so that is output compare. The mode that we are going to be using is this PWM mode. All right, because the main aim is we want to drive our motors. Okay, so that is the mode we're going to be focusing on, but the other modes are also there if you think you want to use them. All right, so a few other things. We have all these counters are 16-bit counters. You can configure them to count up or to count down. Okay, and you can reload with a particular value. Okay, or you can reload, or you automatically reload to either FFFF or 0000. On top of that, you also have a prescaler. The prescaler is for you to scale down the frequency at which you're going to clock the module. Okay, so if you do not want to clock it so fast, all right, you want a bigger time gap, okay, between the triggers, then you can have a higher prescale. Okay, so this is the general configuration of the block. All right, so in terms of firstly is your clock source. All right, so there is a CMOD sort of register or bits where you can select whether you want internal or external clock. In our case, we use internal clock, okay, because we want to make sure the PWM is generated in a consistent way. All right, so we use the internal clock. Prescaler is up to you to decide, okay, depending on the frequency that you want. Okay, count up and count down are all in these registers over here. All right, and when you do count up and count down, all right, there are two ways of configuring it. Okay, you can count up. So when it counts up, you reach this mod value. So this mod value is the value that you count up to when the counter counts. So when I count, I start from 0, then 1, 2. So the counter keeps going up until I hit this value called mod. All right, so it's only up counting. After it hits a mod value, it will go back to 0 and then it will start again. Okay, if I configure up down counting, it will start from 0, 1, 2, go until mod. Okay, after mod, it will come to mod -1. Okay, so it will come down and then go to 0 and then it will start again. Okay, come down to 0 and then it will start again. All right, so it will generate interrupt when it hits mod -1. So in the next clock over here, it will generate interrupt. Okay, so what I'm telling you is basically you have a lot of different options, a lot of different ways to configure it. Okay, in the lab, I'm going to just guide you through one way of doing it. If you want to do it in any other way, it's fine. Right? Any other way is fine. So you do not need to follow the way you're doing it in the lab. Okay, the lab, I'm just going to guide you through the way of configuring it so you have some PWM working. Okay, if you want to change it, go ahead and do it. All right, DMA is another block. We will cover that in a later chapter towards the end. All right, but DMA is also something you can do when you want to, you can enable a DMA transfer to happen when a timer overflow occurs. All right, and there's also a flag that indicates that the timer has overflowed. Okay, so whenever I hit the mod value and overflow, there's a flag that is set. Okay, and of course, as most peripherals, if you configure the interrupts and you enable them, okay, when this trigger happens, you will jump to the IRQ handler. Okay, so this is the basic counter mode over here. So if I want to count external events, so in counter mode, you are trying to count external events. So I need to set it to 10 to select external input, and prescale 000. So this prescale factor is again in certain bit configuration. So there are 3 bits out of a particular register. All right. So you need to configure this prescale bits according to what frequency you want to count in or count the clock in. Okay, in counter mode, generally we set prescale to 0 because you are basically counting events. Okay, so as and when the event occurs, you set the you increment the counter module. Okay, so this is what I mentioned just now in terms of counter mode, all right, and modulo. If I'm doing in the counting up mode, from 0, I count all the way until I hit the mod value. At the end of the mod value, that means when I overflow to 0, at that point, so this point here is where the timer overflow flag bit is set, and I can also jump to the interrupt. All right, so that is how you can configure your PWM to behave. All right, if I'm doing in counting up mode. The other option is the count up and count down. So I'll count up and then I'll count down. All right, when I do count up, count down, the interrupt is triggered whenever I go from mod to mod minus 1. So this is mod value. Okay, and this is mod minus 1. So whenever I transition from mod to mod minus 1, that is where the time overflow bit is set, and then I can jump to the interrupt. All right, so depending on which mode you configure it in, you will generate interval between interrupts, okay, depending on what you want. Okay, so these are all different modes of configuration. Okay, so let me go into the register view. Like I said, I always want to make sure we go back to our data sheet so that we know where to search for information. Okay, so please open up a data sheet. Okay, if you haven't already, okay, open it up. Okay, go to chapter 31. Okay, chapter 31 is our timer PWM module. Okay, so in this chapter, you can look through all the details of the timer module, like what we have discussed over here. All right, so everything is over here. Okay, so let me go into the registers, okay, and I highlight a few of them. So the first one is the status and control register, TPM XSC. Okay, why is there X there? Because it depends on which timer module you're talking about. So how many timer modules do we have? Okay, how many timer modules do we have? Any answer? This timer PWM module, how many do we have? Okay, most of you are saying 2, 3. Okay, so if you want to find out, one of the easiest way is look at the sets of registers. So you can see here, TPM 0, there's one big block. TPM 1, there's one big block, and TPM 2, there's another big block. Correct? That means 0, 1, and 2. That means there are 3 separate timer blocks available for us to use. Okay, so if you're not very sure, just look at the registers. Okay, look at the registers and look at how they are grouped together. All right, and like what I mentioned just now, for each timer block there are 6 separate channels. Okay, so for timer 0, for example, there is channel 0 up to channel 5. Same thing for timer 1 and timer 2. Okay, so before you think of all the things you want to do, again, be very mindful of the fact that what is available at the microcontroller level may not be available at the board level. All right, we always have to be careful that not everything is available at the board. That means we need to see which are the pins brought out, okay, for those header connectors that we can tap onto. All right, so even though we have 3 timer modules here and each of them got 6 channels, that means 18 PWMs. You can make your robot climb like a spider all over the place. All right, okay, but do we really have 18 PWM channels that we can tap onto? All right, so that is a question. Okay, so we need to be mindful of that. So always look back and see which are the PWM modules that I can tap onto at the hardware level. All right, so we will look at that in a while. Okay, so let me go to the first register, S and C register, status and control. So this is where you have to do a few important things. The first one is if I want to enable interrupt, there's a timer overflow, interrupt enable. Okay, and then this is to enable the PWM, select whether I'm going in up mode or up down counting mode. All right. This one is whether I'm going to be incrementing based on every counter clock, and this is on the prescale factor. All right, so when I go through the sample code later, we will see how we can apply this. Okay, then the next thing is your counter register. The counter register holds the current count value. Okay, that means when my counter is counting up, what is the actual value? Generally, we don't need to worry about this because we will already pre-calculate that when my counter reach a particular mod value or certain value, I will generate an interrupt or something, correct? But this basically gives you the actual value while it is counting. This mod register is the modulo register, okay, and this is basically the limit. Okay, so for example, if I'm doing an up counting, when I go all the way to mod, it will overflow in the next clock cycle. All right, so this is the upper limit. If it's up down counting, then it will be 2 times of this. All right. Okay, so the mod value is the value you write to depending on what is the upper limit. For example, if you're doing an up counting. Okay. Okay. This registers C and SC, we will come back to this later. All right, when I'm going to talk about the PWM. But these are the main registers that you see that you need to configure. Okay, in order for you to configure the approach based on that sort of desire that you want. Okay, so there's a question here, why are there many reserved bits? Okay, so generally most microcontrollers have reserved bits, okay, for a few reasons. Okay, one is when they release a microcontroller, they will release many variations of that same microcontroller. Okay, so ours is this KL25Z P80. Okay, so we have this long for sort of part name, part number. All right, and if you look at the data sheet, there will be a few other variations that are slightly less complicated and some that are more complex than this. Correct. So this reserve could be that they are used by the other variations that have more capabilities, more features. Correct. Because if you look at it from the business perspective, it's a lot of money and time and investment to come up with a new processor hardware design. Correct. So in order to maximize their profits, they will sort of provide different variations of that same hardware to cater to different markets. Okay, because not everybody wants a very high-end controller with so many features. So for some people, they like the controller, but they don't want so many PWM, so many features, so they will take a lower end version of it. Some people want more, they take a high end version of it. Okay, so that is one reason why some of the bits could be reserved. In some cases, they are also reserved because they are planning ahead for future architectures that are not yet released. Okay, so they have a design. Okay, they do not want to sort of reinvent the whole wheel, correct? So they want to leverage on the current design for future architectures. So by setting aside more reserve bits, they are sort of putting a placeholder in play there so that when I have more ideas, more things I want to implement, I already have certain bits reserved for me for all this configuration. Okay, so these are the general reasons why you see a lot of reserved bits. Every microcontroller, in every microcontroller you will see this. Okay. Okay, so let me come back to our slides first. Okay. Okay, this register here, TPM config, we don't necessarily need to use most of it, except for the case where you're going to use it for counter operation. Okay, but in most cases we're not going to be using this so much. The other register is the status register. This status register is the one that holds the flags. Okay, if you remember just now I said that when there is a overflow that happens, the flag is set. Now, do we need to check this flag explicitly? Not necessary, because as long as interrupt has already been enabled, then I will automatically jump to the IRQ handler. All right, so these flags would be set, okay, if I'm intend to manually poll for this event to happen. Okay, but in most cases, since we already have interrupt, we rather use interrupts to handle these overflow or underflow events. Okay, so in terms of the channel mode, like I mentioned, there are 3 types of channel modes available. Okay, the first 2 are for different type of use cases. The input capture mode is, for example, when an input signal changes. All right, then I want to capture it. Okay, so for example, I want to measure the duration of a pulse. Okay, so I can configure the input capture to trigger on both rising edge and falling edge. Correct. So when the rising edge happens, I capture the time. Okay, then the falling edge, again, I can capture the time. Then I know the duration. All right. So of course, you can say that, hey, I can also do this in a GPIO pin. Correct. I can configure GPIO pin to trigger on positive and negative edge. Then in the interrupt handler, I can go and process this information. Also can. All right. But your timer module also already has this capability, and it already gives you a count value, which means the hardware is already doing the back end counting for you. So you just need to know the starting value, ending value, and then based on your prescaler settings and your clock frequency, you can immediately know the elapsed time or the duration of this pulse. Okay, so that is input capture mode. The other one is output compare mode, where you can say whenever my output signal reaches a specified value or output, I can modify output signal. Okay, so I can say that when my counter hit a particular value, okay, then I toggle. Then again, when it hit another value, again I toggle and toggle and toggle. All right. So this is again achievable through other means. Correct. If I just go back to what we did earlier, the programmable interrupt timer (PIT), that also I can use this. Correct. I can just set the programmable interrupt timer to count for this particular duration, and every time the interrupt is triggered, I go and toggle the GPIO. Correct. Okay. So why do we still want to use this? Because in this case, the registers already configure this behavior for us. Okay, allow us to predetermine this behavior by just configuring the registers. All right. So as long as I configure everything, and these events happen, the output will just toggle by itself. Correct. If I were to use the PIT approach, for example, then I can still achieve the same functionality, but in the IRQ handler, then I have to go manually execute the code to toggle the bit. All right. So it is just different ways of doing the same thing. Okay. So you need to see which one works for you, which one is better, or which is available at that time. All right. And the one that we'll be doing in the lab also is what is the PWM to just generate the required signal for motor control. Okay, so in terms of PWM, you have this important register that you need to configure, TPMXCNSC. All right, so these bits I will go through in more detail when we are looking at the code. All right, but basically these are the register bits you need to be configuring correctly when you want your PWM to come out. Okay, and this CNV register is the 16-bit value for output compare or input capture. So in our case, we are not going to be doing either of this. So we're going to look at this register for in this case. Okay, PWM, I do not need to go through so much. Okay, we know that the whole idea is you use a digital pulse, okay, to create an equivalent analog voltage. Okay, so that is the whole idea of PWM. Okay, so the details of it, I think all of you know, right? So we don't need to go through that. Okay, in terms of counting behavior, this is important. The period is basically the mod register. Okay, the mod register is the one that controls the entire duration of the PWM, and the pulse width. Okay, pulse width is the one that controls the CNV cycles. Okay, so this slide is based on the count up mode. Okay, so in count up mode, basically what is happening is you're going to count up to a particular value, then reset to 0 and count up again. All right, and this duration here is based on the mod register, the entire period. All right, but the pulse width, that means at some point of time I want to hit a particular value, that is the CNV register. So this point here will determine the register configurations here will determine on whether I have high true pulses or low true pulses. That means, is my waveform going to look like this, or is it going to look like this? All right, that means when I'm counting up till I reach CNV value, is it going to be 1 and then 0, or is it going to be 0 and then 1? All right, so that is these are two registers you need to configure, the mod register and the CNV register, to decide the pulse duty cycle of your PWM. Okay, so we'll be seeing how to do that. Okay, if I'm doing it in center align PWM, center align PWM is the one that is using count up and count down mode. So in count up, count down mode, the entire period is 2 times the mod cycles. Okay, 2 times the mod cycles. So in that case, you can see that the period is double and the pulse width is also double. Okay, based on the CNV. All right, so I will count up and then I'll count down, and then when it's 0, again I'll go count up and count down. All right, so again, the configuration of these registers here will determine whether I have high true pulses or low true pulses. Okay, for our project, so far, I think most of the students have used the count out mode just by itself, and it seems to work fine. Okay, it's more than enough for our PWM requirements for the motor. If you want to try the count up, count down mode, also is fine. All right, but I think the countdown mode alone has worked well so far. Okay, so let me go over this week's lab. All right, and make sure you understand what to do. All right, so let me stop this first. Okay, so this week's lab is on PWM audio. Okay, so there's two things we're going to be doing. One is the PWM generation, and also how we're going to generate the audio. Okay, so if you look at the project requirement, you are supposed to play music, okay, continuously from the moment your robot starts the sort of computation run. Okay, and you are free to choose any music. The previous batch, that means the one before last semester, 2 semesters back, I fixed the music to Baby Shark, and everybody was so sick and tired of Baby Shark by the end of the module. Okay, so this time now I decided not to make you all go through that same torture. Okay, so I last semester I changed it to you all choosing your own song. Okay, but of course your audio that you generate must sound like the real song. All right, so that you need to sort of demonstrate that in the final competition run. So you need to play the real song, and you need to play the tune from your robot, and you must sort of be able to say that it's the same. All right, then it's fine. Okay, so for PWM, we're going to be initializing the PWM module. So this is the code. Let me go through the code step by step with you so you understand what we're doing. Okay. Okay, so the first thing is we are going to be using let me see which module. Okay, so we are going to be using timer module 1. Okay, timer module 1. All right, and here you can see that I have done a few things here. Okay, first thing is you enable port B clock gating. Now this is another thing that you should take note of. Most of your peripheral subsystems are multiplex, okay, with the port pins. All right, and because the multiplexing configuration is done through the port-based register, you need to enable the port power as well. All right, so even though we're not using that function for port, we're not using that pin for port functionality, you need to enable the power to that particular port because you need to configure those registers that will then switch the multiplexing for the desired operation. All right, so this is the important thing that you may forget. Okay, so even though we are not using the port as a port pin, we still need to enable power to it. Okay, so once I enable power to it, there's two things here. Configuring the PCR register with mux3. Now, what is mux3? So if you come back here, okay, so you can see that for PCR register, the mux here, when I say mux3, I'm selecting alternative 3. So what is alternative 3? Okay, what is alternative 3 over here? So in order to know what is alternative 3, I need to look back at the mapping. Okay, I need to look back at the mapping. So let me look back at the code here. So what are the pins? Port B0 and port B1. Okay, so port B0 and port B1, both I am configuring them for alternate function 3. So where do I get this information? So I need to come back to my data sheet and go to the mux. So the multiplexing configuration section is here, chapter 10, signal multiplexing. So if you scroll down here, okay, so you can scroll down till you find port B, 0 and 1. Okay, so you can see here port B, 0 and 1 is here, and for timer module 1, channel 0 and channel 1, this is alternate 3. Okay, so that is the reason why we have to do this. Okay, the reason why I'm giving you all this is I think some of these things takes a long time to figure out. Okay, especially if you're new to a controller. So if I don't tell you this information, you will spend a lot of time trying to see where is this mapping and all. Okay, so that is why some of this information I'm giving you upfront, so you don't have to spend so much time. But at least now you know, in future when you want to use some other peripheral block, you will know where to go and look for this. Okay, so in our case, we're going to use port B0, port B1, and the alternate 3 function for that is timer module 1, channel 0 and channel 1. Okay, so that is the reason why we have chosen this configuration here. Okay, so that is the first part. We enable power to the port and we configure the port pin for the correct multiplexing function, and then we enable clock gating. Okay, for timer 1, since I'm using timer 1. Okay, next is I want to select the clock module. Okay, so this clock module is based on what is the clock I want to sort of run my peripheral block. So there's a few different configurations. Let me try to find this over here. Okay, so in this TPM SRC is the TPM clock source. So you can see that for different some of these peripheral blocks here, you can also select which clock is going to drive these peripheral subsystems. Right, so you can have a UART block clock by some other source, the PWM clock by another source, DMA clock by another source, and so on. So, like I said, there's a lot of variation here. Okay, so I'm giving you one option that I've already calculated and I've done everything. All right, you want to change it, you can change it. All right, so it's just an option. Okay, so in this case, I'm using the NCG FLL clock. All right, which is going to drive the whole system. Okay, and for my case, I am using the 48 megahertz main clock. Okay, and let's come back to this first. Okay, let's look at this first. TPM1 SC register. Okay, now in this SC register, I am setting my CMOD to 1 and my PS to 7. Okay, so CMOD to 1 and PS to 7. So let's look at that. Okay, let me come back to this. The TPM SC. Okay, so I'm setting my CPWMMS to 1. Okay, 1 or 0. So CMOD to 1. Where is CMOD? CMOD to 1. Okay, so LP TPM counter increments every LPTM counter clock. All right, that means basically every time there's a clock coming in, I will increment my counter. All right, and this is set to, I've not done anything to this particular bit. That means it's going to operate in the count out mode because this is not configured. And the other configuration here is PS7. So PS7 means it is 1 to 8 prescaler. Okay, so I'm using these current settings for my code over here. And with a prescaler of 1 to 8 and my clock at 48 megahertz, that will give me a frequency of 37,500. All right. Now, the mod value is the highest value. Okay, that means this divided by 7,500 in this case will give me a frequency of 50 hertz. All right, so by putting my mod value, that means my mod value, if you remember, when I'm doing outcount mode, is the maximum count I will reach, which will determine the period of my PWM. All right, so once I hit a count of 7,500, I will flip over to 0 and start again. And since I'm clocking my TPM module at this particular frequency, all right, in order for me to flip over, the total time elapsed would be based on a 50 hertz signal. All right, so these are the configurations based on this timing, and these values are calculated. All right, like I said, if you want to change them, go ahead and do it. All right, if you want to use a different configuration for your PWM module, you are free to do it. The last one is this, to enable the PWM. To enable the PWM, you have to remember that each module has 6 different channels. All right, so each of them has a C0, C1, C2, all the way to C5 SC register where you need to do the configuration. Okay, the earlier configurations here are generic. Okay, okay, so there are questions about the mod and the modular number. Okay, wait, I'll come to that in a while. Let me finish this first. Okay, I'll come to those questions in a while. Now, this last part here, the configuration is channel 0, channel 1. Both of them, I set your ELSB and MSB to 1. Okay, so what does this do? Let me just show you first. Okay, so the MSB and MSA. So if you look at it here, here the MSA is 0, or I'm only setting MSB, so it's 1 0. So when it's 1 0 here, I'm doing H align PWM. All right, because I'm only doing in count up mode. And ELS B and A 1 0. So only the B is 1, A is 0. Okay, so B is 1, A is 0. So that will make sure it is a high true pulse. That means initial will be high, and then once there's a match, it will go to low. All right, so that is basically the configuration. Okay, and what you need to do is you need to put the appropriate values into the COV register. Okay, the COV, the O in this case, if you look at the data sheet, they say CNV. The N is the channel number, so channel 0 or channel 1. So in this case, you can put a number that you want to hit so that you will be able to achieve the desired duty cycle. So the mod is the period, and the CNV is the duty cycle. Okay, so that is basically the things you need to do. So as far as the main code is concerned, once I initialize the PWM, okay, that means I call this function to initialize all these registers, and I set my CNV registers, I don't need to do anything else after that. All right, because everything else is automatic. The system will just keep running, and it will just update, okay, based on the settings that we have here. All right, so let me just look at the questions again. Okay, the period mod plus 1 is actually the edge aligned PWM, which is what we're looking at over here. Okay, the reason why I say mod plus 1 is because it's 0 up to mod. All right, so if I say mod is 4, means it's 0 to 4, so it's 4 plus 1, 5 cycles. Okay, what's the difference if I pick a different modulo number? If you pick a different modulo number, basically means that your entire period of your PWM will be shorter or longer. Okay, so there are two numbers. One is the two registers. Mod is your period, CNV is your duty cycle. All right, so these are two important things. Okay, so there is no, as I said before, for this semester there is no lab report, only lab demo. Okay, so it's 10 o'clock. I'll give you all a break now. Okay, I need to set up the hardware to show you how it works. Okay, so we'll take a short 5 minutes break. When we come back, I will show you the demonstration, and then we can wrap up this chapter and go on to the UART chapter. Yes, for me, my clock is changed to 48 megahertz in the header file. The header file changing is, let me show you here. Okay, so inside your system MKL25Z4H, there is this hex defined clock setup. All right, if you change it to 1, okay, you can see down here, the default value is 0, okay, which means you will run at 20.97 something megahertz. By changing it to 1, you will run at 48 megahertz. Okay, so again, if you do not want to change your system clock, you want to keep it at default 0, then the numbers here will change. Okay, the calculation will change. All right, but everything will still work. It's just that you need to look at how to calculate the numbers differently. Okay, we need to use two channels because you have, at the bare minimum, you need to control the right side and the left side of the robot. All right, so one channel for the right side, the other channel for the left side. Whether you want to split it to both the right motors and split it to both two left motors is something that you can decide how you want to do that. Okay, edge align and center align are basically the same thing. The only difference is edge align gives you a wider So a better resolution in the sense that you have a bigger count, okay, in terms of your period. All right. So in our case, either I did not try center align for our robot so far. I only use edge align, but it all depends on what is the period you want, okay, for your whole PWM. If your edge align already is good enough, then we can stick with that. Okay, so it's just a matter of the timing resolution. Yes, each timer module has 6 channels. So each channel can be configured to operate differently. Okay. Okay, so I think I've been talking in the break as well. Okay, so please go for your break. We will come back in a few minutes and then I will show you the demo and then we can wrap it up. Okay, and go on to the next chapter. Okay, so let me come back to show you how to connect it up. Okay, so since we are using port B0 and port B1, okay, so since we're using port B0 and port B1 in this case, we need to check where is that. So if you look back at your lab from here, the layout over here, port B0 and port B1 is on this upper right corner, these 2 bits over there. Okay, so we need to tap onto them. So of course your scope, you need ground. Okay, so where is your ground? So you, oh sorry, it's over here. Okay, so it's on the top. Yeah, so it is equivalent to the top, top right over here. Okay, and then we need a ground as well. So which ground can be used? So we can use the grounds available. So one ground is the one on the bottom left over here, the pin 14 on the bottom left. We can also use the ground over here, okay, on the right side. Okay, so let me connect up and just show it to you what you're supposed to see. So you can have, okay, so those are the 2 pins connected over there. So you can see over here. Okay, so you can see that the port pins over here, port B0 and port B1. Okay, over here, and then the ground one is here and one is over here. Okay, so you can use that. Okay, so let me run my code and then you can see. Okay, so you can see 2 waveforms there. All right, so one is 50% duty cycle, the other is half of that. Okay, so that is basically because of the setting I put here. So you can see here that for one of it, because my full period here is 7,500, all right, in terms of count, all right, timer value. So half of that is 3750. So when my timer hits 3750, I want it to toggle. That means in terms of completing the high cycle and going over to the low cycle. So that is the value you put in the C and V register. All right. In my C1V register, I half that some more. So that is why I see 2 different duty cycles over here. One at 50%, one at 25%. All right. So in this case, you can see that I have not, if you look at my entire code, there are no interrupts here. Okay. And you do not need interrupts in this case because once you configure the PWM, okay, and you have put in the values, they will just run automatically in the hardware. All right. You can configure interrupts, okay, if every time you complete one cycle, you want to do something else, okay, or you want to get update some other variable or something like that, then you can use interrupts. Okay, but if your objective is just to run the PWM signal to drive the motors and you don't need anything else, then you can just configure them. Once the timer values are written and enabled, they will run automatically. Okay, you do not need interrupts in this case. Okay. So that is basically what you're going to do for the lab. Okay, so once you can see these PWM signals, all right, then you know everything is set up correctly. Then you can go on to using them for your to generate different frequencies for your musical notes. Okay, so I provided some notes there. Of course, online you can also search for all the in-between notes. Okay, all the sharp, the flats, everything to get all your musical notes that you want. All right, so that is what you need to do for this lab. Okay, so let me stop this. I will go on to the next chapter first. Okay, if at the end there are other questions that you still have doubts about the PWM or UART, you are free to ask me after that. Okay, so let me just go on first so that we can. Okay, so this serial communication is again another important topic. So why is it important? Because in your setup, okay, so you have an Android app. Okay, so I hope all of you have already started to explore the app, creating it. Again, if you do not want to use the AI2 platform, you want to use any other platform, it's up to you. All right. And those of you who, the entire team is fully Apple fans and don't have any Android devices, you have to look for some other way of doing it. Okay. So you can exploit it. There is one thing that I came about recently called Thunkable. Okay, I'll send in the link as well. They seem to support a very similar platform as AI App Inventor. Okay, and they support Apple devices as well. All right. The only drawback I think is if you use the paid version, they do not allow you to package it as a standalone app. It still has to be sort of running off your PC, something like that. All right. So you can explore this as an option if for those of you who do not have any Android devices in your entire group. Okay. So your Android phone is supposed to pair with your BTO6 module. Okay, you're given a BTO6 module, so you're supposed to create your Bluetooth link over here. And once you pair your Android app with your BTO6 module, what comes out of the BTO6 module? Okay, so of course there is power, there is ground, okay, and then there is data. And this is your serial data. Okay, and this serial data will then be connected to your microcontroller's UART module, okay, on the receive pin. Okay, there is no need to transmit anything back to the app. Okay, but when the data comes in, it will come in through the UART module receive pin over here. So that is why the serial communication is important. Okay, so this module, so for next week's lab, there are a few parts to it. One of it will actually require you to have some app prototype running, integrated with your Bluetooth BTO6 as well, to make sure that the whole setup is working. All right, so if you have not started on your app creation, okay, please try to do it this week, okay, so that when next week's lab comes around, you are ready to put everything together. Okay, so as you can see, we are building up all the subsystems progressively week by week, okay, so that your project is actually getting built up. All right, of course, you still need to assemble your whole robot and figure out what you want to put where and so on. But in terms of functionality, we are building up everything. Okay, so with the PWM module covered, you can proceed to fix up your motor control aspect. Okay, and with next week done, your interfacing is done. Okay, in terms of Android app to the UART, and then the rest is integrating the OS inside. Okay, how you're going to create a multi-threaded environment where everything will then run. All right. Okay, so we're going to be covering, so in terms of serial communications, we have seen UART before in your EPP module, okay, and Arduino Uno and so on. There are of course other equivalent serial protocols such as SPI and I2C. Even though we're not covering them, they are very commonly seen everywhere. Okay, and of course it's also good to understand the idea and the details behind it. Okay, so you know how they work. Okay, but in our case, we're only going to be covering the UART. Okay, so just a quick uh, sort of primer on why we need to communicate serially. Okay, maybe about 25 years back, if you were to buy a printer, okay, that printer would come with a huge cable. Okay, a very thick cable with like 40-50 pins like that. All right, and you need to sort of stuff it into the back of your desktop just so that you can send a print job. All right, so that was the kind of wiring challenges we had to deal with in the past. All right, because everything was parallel. All right, then of course along the way, when we have improvement in serial communication, things help a lot better. All right, now so in terms of a microcontroller perspective, by trying to communicate in parallel, what happens is you will end up having as many lines as you need depending on how big is your data bus. All right, so imagine, you know, you have 4 peripherals, each of them having 8 bits, you know, and each of them having a read-write signal and so on. You have 40 pins just to communicate with these peripheral devices. Right, so it's not practical at all. Okay, if you move on to a parallel bus interface, you still need at least about 10 pins for the data and read write plus chip select pins for the different peripherals. All right, so even though it's an improvement to go to a parallel bus interface, you still need a lot of data lines. Okay, if you have 16 data lines, 32 data lines, it just becomes crazy. Okay, so by moving to serial, definitely things are a lot better because then you just need one serial data line, all right, and maybe one more clock line. Okay, so in this case, as you can see, with just one clock and one serial data line, you can automatically get data to be transmitted and received between devices. All right, of course, internally in the hardware, you have shift registers and clocks. Okay, so that is the digital design perspective, but we're not going to go into that. All right, so as long as we know how the system works in terms of clocking and data, then that is good enough. All right, there are different ways of performing this serial communication. One is, you call it synchronous full duplex. All right, in full duplex, you can transmit and receive at the same time. All right, so you have 2 separate data lines. Okay, so technically you can do transmit and receive concurrently, okay, across the different devices. The other one is half duplex, where you can transmit or receive at any point of time. All right, so it all depends on the peripheral you're dealing with, all right, and of course what kind of mode they operate in. All right, so this additional thing here, this select, so this is the what we call the chip select lines, CS line, chip select. Most devices would have some form of chip select pin that you need to activate in order to talk to the device. All right. In our case, since the device we're talking to is the BTO6. Okay, BTO6 does have a chip select, but I think it's already enabled by default, so you do not need to connect it. All right, but if you were to manually toggle it, okay, depending on whether you want the Bluetooth or don't want the Bluetooth, then you need to have a separate GPIO pin to be connected to this chip select line. Okay, in terms of asynchronous serial communication, basically what happens is you eliminate the clock. So all the while we saw there was a clock there. All right, so in asynchronous communication, you can eliminate the clock. All right, so the clock then needs to be generated locally. All right, so of course then it adds other challenges in a sense that the transmitter must always add some indication, okay, that is beginning to send the data, so that is usually the start bit. All right, and the receiver must be able to detect this start bit and then know when to start sampling. All right, and once the data packet is complete, you must also send a stop bit. All right, and of course, since both the clocks are generated locally, they must also be in the same frequency. All right, so you need to pre-configure both the transmitter and receiver upfront to operate the same frequency or same baud rate, and then it will work. All right, if any mismatch in the settings, you will send something, but the receiver will interpret as some garbage. All right, you will not be able to get it correctly. Okay, so in terms of data frame for serial communication, most controllers have a few variations. Okay, some can transmit LSB first or MS bit first. Okay, and which configuration you choose. Okay, the clocks being out of phase is not an issue, because as long as it is able to detect the start bit, the hardware internally will know when to sample next. All right, so you will know that once I detect the start bit, at what time interval later I need to sample again. So it will sort of readjust based on the arrival of the start bit. Okay, most microcontrollers have varied configurations, LS bit or MS bit. I think Arduino Uno also has that. Data size packet 7, 8, 9, these are all common configurations. Parity bit is again for error correction. You may use it, you may not use it. Baud rate, again, you have quite a few standard baud rates. Most devices by default, you should have a basic operation speed of 9600. Some devices may be able to go higher. All right, but 9600 is quite a standard setting that almost all serial devices support. Okay, and it's a very simple network sort of protocol without going into any complicated overheads. Right, so we will not go into anything else other than the basic idea of doing it. Okay, error detection is something that I think most of us have seen before. The parity bit is basically the additional bit, okay, that you add in depending on the configuration of whether you're going to be using odd or even parity. All right, so for example, if I send this data packet over 0111 0111, okay, and I send this over, this is the transmit, okay, and over the receive side. Okay, if I say this is even parity, then what is the additional bit I must append here? Must be 0, correct? Because even parity means I must have even number of ones. All right, so since there are already even number of ones, I say 0. So over at the receive side, you will expect to receive the same data packet. So if everything goes well, okay, what it will do is you count the number of ones together with the parity and check it's an even number. All right, so if everything goes well, no issues. But what if one of the bits flip? Okay, so if this is even and this also must be converted to even, then it will say that this is 5. So it's odd, so something is wrong. All right, so it can detect error. The other, of course, the other issue is it doesn't detect even number of errors. So if this bit flip and this bit also flip, okay, so you have 2 bit flips, then it still says it's even, then you will think it's correct. Okay, so it is a very crude mechanism, okay, and for simplistic systems it is fine. All right, but of course, if you suspect or you expect there is more noise on your transmission line and more chances of error, then definitely parity alone in this application context is not good enough. All right, so you need to look at other mechanisms, okay, like what you have seen before in EPP. All right, so let's look at the software side on how we can do this. All right, so we need to firstly understand that this is an asynchronous sort of communication because the controller does not know when the next data packet is going to arrive. Correct? Okay, and we need to be mindful of that. So we need to make sure that the serial communication is set up correctly to capture data the moment it comes in. All right, and of course there are 2 approaches: polling and interrupt. And I think almost everybody will use interrupt. okay, because that is the most effective way of capturing the data the moment it comes in. All right, so okay, the rest of these slides we are going to be talking about sort of an approach to writing a library code to handle serial data. All right, you don't necessarily have to use this, okay, in your project, okay, but it's just one idea of how you can create a structure to handle transmit and receive of serial data. Okay, so in this case what you have is you have a main program, then you have transmit ISR and receive ISR, okay, where you execute depending on whether you want to transmit or receive. And of course, if there's error also, you want to handle the error. All right, so one way of dealing with it is using this thing called a circular queue. All right, so a circular queue is a useful way of buffering information so that both the transmit and receive can sort of write and read from a common buffer. All right, but you need to manage this buffer correctly. All right, so that is what we're going to be looking at here. Now, in our Cortex M0 that we are dealing with, we only have a single IRQ handler. Okay, this is important. We do not have separate interrupt for transmit or receive. It's a single interrupt, all right, for the UART module, and inside the handler, we must sort of differentiate what triggered the interrupt. Okay, is it I want to transmit and then I trigger the interrupt, or I receive and then it trigger the interrupt? In this project, it is a bit easier because you know you're only receiving data. Correct? Your Android app is going to send data through the BT06 module and you're going to receive it. Okay, so there's nothing to send back. So in that sense, it is a bit easier. Of course, if you're going to use this board for other projects in the future, you must be mindful that it is the same handler that will be called for both transmit and receive events. Okay, so in this case, all right, what we have is we have a common sort of a queue or a circular buffer, and what will happen is you have a transmit queue and RX queue that will increment or decrement the pointer. All right, and you need to wrap the pointer at the end to make it a circular buffer. At the same time, you need to keep track of when the queue is empty and when the queue is full. All right, so here you have to see that even though I write it as two separate ISR, it's actually the same handler. Only thing is you have different code within the same handler to handle the two different events. Okay, so this is a definition of how you can create a queue. So you have a structure, okay, where you create a buffer here. So in this case, my queue size is 32. All right, and then I have a head and a tail. So this is a index. Okay, so these two are the index of where is my head and where is my tail. All right, in terms of the buffer. So the head is where I read from, and tail is where I add to. All right, depending on transmitting or receiving data. Okay, at the same time, the size. Okay, how much of the space I've already used. Okay, and I create two structures here. Okay, two variables txq and rsq over here. So over here, what do you see? You can initialize a queue, all right, by calling this queue unit, all right. And so in this example, what we have done is we have set the initial value of the data inside the queue to be 0, and we set the head and the tail and the size all to be 0 first. All right. And these two functions here are to basically check whether the queue is empty or queue is full. Okay. So if the queue size is equal to 0, that means it's 0, that means there are no elements in the queue, then you will return true. Correct. If it is equal to the queue size, then you know it's full. All right. So these two functions are there to help us to check whether the queue is empty or queue is full. All right, then comes the two important functions on when to enqueue, when to dequeue. All right, so when I have this queue over here, all right, so when I call the enqueue function, okay, so for example, this is my head, initially this is my head and this is my tail. Okay, so when I want to enqueue means I want to add information, okay, to the queue. All right, so I first check that the queue is full or not. So if it is not full, okay, then what I can do is I can take the current data. This is the new data that I passed in, all right, when I call this enqueue function, and I add it to the tail. Okay, so I add it to this tail here, and then I increment my tail. So my tail from here will now point to here, point to the next empty space. All right, and then of course this is to do the wrap around, and then I also increment my size. All right, so if everything goes well, our return is successful. So I've added one element to the head. Now for DQ, again I check whether it's empty. If it's not empty, wherever the head is pointing to, I take this data and I pass it to my variable t, which I will return. So this variable comes, or this data will come out to my variable t, and then I will return it. Okay, and once I take out the first data, I will again increment my head. So my head will then point to the next location here. All right, so effectively, this structure allows you to deal with kind of a peripheral block where you may have multiple sets of data coming in, but you may not read it at that rate. You may read it a bit slower. Okay, so what you can do is this sort of circular buffer helps you to buffer in the data, all right, and then later on you can read the data. Okay, do we need this for the project? Okay, it is not necessary. Okay, why? Because in our case, you are going to send one command at a time. Okay, so if you want the robot to move forward, you send a move forward command. You want it to play music, you send a play music command. So you will send commands one at a time. Okay, and then you will sort of decode the command and interpret it. Okay, so it's not necessary to use this circular buffer approach for the project. Okay, in the project, you can just set up your interrupt to receive this incoming data packet, and once you receive it, you decode it, and then you call the appropriate function or activate the appropriate thread to perform the action. Okay, so this is just a idea that you can use, but it's not necessary. Okay, so to send data, you call enqueue. To receive data, you call dequeue. Okay, so this is just an example only. Like I said, you don't need to implement it, but you can if you want to. We will be looking at this in the tutorial, okay, to discuss a bit more about this. All right, but you don't necessarily have to do it. You don't have bonus marks for implementing something like this. Okay, it is a choice. Correct. So it is a choice. The assessment matrix you already have. Okay, so in terms of functionality, as long as it is there, then you can fulfill the checklist and you can demonstrate everything. All right, then I think that is good enough. All right, whether you want to take this approach or another approach is up to you. Okay. Okay, so do we need separate buffer or same buffer? You actually only one circular buffer for both enqueue and dequeue. All right, so it's the same buffer that you will point to for both enqueue and dequeue. Okay. Okay, in terms of passing messages. All right, so in your Android app to your in your Android app for your that you will send over the data, you will actually be configured as 8-bit data. Okay, and this 8-bit data that you receive, okay, if you want to try different ideas, is up to you. All right, But one of the things which you will try in the lab next week is, when I send this 8-bit data, how do I interpret this 8-bit data? So that is again something that you can decide. Okay, so when I look at this 8-bit data, you can set aside certain bits to represent whether is it a motor control, or is it audio, or is it LED, and so on. All right, and then some of the bits could be the actual value. All right, so you can decide how you want to pass the data to represent the information that you're dealing with. All right, so there is no right or wrong here. It's a design choice, okay, that you have to make. Okay, so let's come to this again. In terms of what is available for us. Okay, what is available for us to use. So you can see the color coding here. In terms of UART, there are a few different pins. All right, so when you are doing the PWM and you're doing the UART, and then you look at the other requirements of your LED and so on, you now need to make some design choices. Okay, which UART do I use, which PWM do I use, and which are the pins that are then available for GPIO functionality for the LEDs and so on. Okay, so you need to come up with a plan, all right, to separate out all these different requirements and see what is the mapping. Okay, so in terms of UART, you can see I have a few options. All right, so which one can I use? All right, so in terms of SPI module, UART module, you have 0, 1, and 2. You have 3 modules over here: UART 0, UART 1, UART 2. Okay, which you need to enable in the SCGC register. All right, but important thing here is, okay, these 3 slides. Okay, I think this 3 is a bit repeat from what we have covered, so I will not go through this again. So I'll come straight to here. In terms of the UARTs, the UART 0 is not available. Okay, because when you are plugging in your KL25Z in your debug mode, you are using that UART 0 module. So the only thing available is UART 1 and UART 2. Okay, so it is good enough for us considering our application. So you do not need to be concerned about this. So you have 2 UART modules, you only need to use one of them. So you need to see which one you want to use. And if you don't use the other one, what do you free up? Okay, so let me go through some of these transmit and receive over here. So the UART transmitter, again, there are a lot of registers here that you need to configure. In general, all serial interfaces use shift registers to shift data out and shift data in. All right, the direction of shifting you can configure LS bit first or MS bit first. If you want to add parity, you can configure parity. All right, at the same time, you can also configure interrupts, okay, with the appropriate sort of flags or registers being set. Then another important thing is your baud rate over here. So all of these are configurable with the various registers that we have. All right, and that will allow us to configure the behavior of the UART module. Same thing for receiver. You have a baud rate generator. Okay, you have received data over here. You can generate interrupts. Okay, and once you receive the data, you can read it. Okay, from the data buffer over here. Okay, so as always, there are registers to be configured. The clock gating, the GPIO configuration in terms of multiplexing. All right, and once that is done, the actual configuration of interrupts and all this stuff. Okay, so another thing is we have the microcontroller itself does oversampling of incoming data. So when you set a particular baud rate, it actually oversamples, okay, to have better noise immunity. Okay, so it does its own oversampling and takes a majority vote. Okay, so whether it's majority 1 or majority 0, and then from there it will decode and tell you whether it's a 1 or a 0. In our case, since we are using UART1 and UART2, they have fixed 16 times oversampling. Okay, why this number is important is because when we set the configuration, we need to take this 16 times into account. All right, so that is why we need to know this. All right, so the baud rate generator, okay, needs to make sure that when we need to divide the module clock frequency down by taking baud rate multiplied by the oversampling factor. Okay, so this is the formula we need to use. Okay, so this divided by 16 is something unique over here because of the oversampling. Okay, so this oversampling is done by the hardware. Okay, so that is why when we calculate the baud rate, we need to take this into account and divide by 16 again. Okay, so that is why, for example, if I'm running at 24 megahertz and I want to operate at 4800 baud, then I need to take 24 megahertz divided by 4800 times 16. Okay, so that will give me the value to write into the baud rate register. Okay, so the coding one, we will look into it, okay, in the example code. All right, but this 16 is something that is again unique to this particular system here. Okay, so when can we transmit the data? We can transmit the data when the data buffer, transmit buffer is empty. All right, so we can poll for a flag, okay, transmit data register empty flag to know it's empty, and then we can transmit data. When do we know it's full? When we can poll the receive data register flag. Okay, so when that flag is set, we know that we have received a byte. Okay, as always, in our case, we are only doing receive. So as long as we configure the interrupt for receive correctly, we will automatically jump to the IRQ handler to take this data in. Okay, so the rest of these are the UART control registers. All right. Again, for these UART control registers, we don't need to worry about everything here except that whether we want to use parity. You can use it, all right, but it's optional. The other one is more important is this, which is the interrupts. In our case, this is important because we want to make sure that the moment you receive a data, we are able to generate the interrupt. Okay, in the next week's lab, we are going to be doing transmit and receive, all right, just to test it out, but we only need to make sure that the receive is working well, all right. Yeah, so that is in terms of this UART control register 2. For status register 2 is for us to know when events have happened. So this is the receive data register flag. Okay, we do not need to read it, okay, because the interrupts will be triggered once this event has happened. So we don't have to worry about it. Okay, what is important is error. Okay, we need to make sure if there are any errors, how do we handle the error, all right, and how do we clear the error if there's anything. All right, so we will look at that when we are examining the sample code. Okay, so the rest of the slides on the configuration and the demo, I think I will leave it for next week. All right, so I think this week we have covered the important concept part. All right, so next week, so the PWM and the sample code that is important for this week's lab. All right, so next week in the lecture, I will go through the code for the UART module just to make sure that you understand what you're going to do in the lab, and then anything that will be easier for us to handle. All right, so for this week, as long as you understand the PWM part of the code, I think that is more important. All right, so just give me a minute here to check on the Okay, so let me just double check and confirm the budget. Just give me 1 minute before we go. Okay, so okay, yeah. So each team has an additional budget of $40. Okay, so the $40 you can buy one additional freedom board if you fry yours. All right. Other than that, not many teams use it to buy anything actually. Uh, One thing, of course, most students say is the buzzer that is issued is so beautiful, the music, that they cannot stop hearing it, so they wanted to get a new speaker. Okay, so that is one thing you can consider if you want uh, a different type of audio quality. Okay, but in terms of functionality wise, you do not need to buy anything to fulfill any functionality. Whatever equipment that's already been issued is more than enough to fulfill all the product requirements. This $40 extra is if you think you want to, it's just a buffer in case your board gets damaged, or if you think you want to buy one or two additional things to just make it look nicer, all right, or sound nicer. All right. The other thing is the LED strips. Okay. You all were issued the LED strips as well. Let me see where is it. So this is the LED strip I'm talking about. This small one over here. All right. So this one is actually a bonus gift. If you want to use it, you can use it. It sort of has, I think, about 10 LEDs already built in there. Okay. This was not part of the budget. All right. So basically, what happened was last semester, one of the labs in engineering was closing down, and then they had a free for all. So whoever could go in and grab whatever they could just went in. Okay, so I just went in and grabbed whatever I could. So this was one of it. Okay, uh, so these LEDs are for y'all to use. If you want to use the separate LEDs, the individual LEDs also is fine. You want to use LED strip also fine. All right, so you just need to go and do some testing to see which one is positive, which one is negative, and then you can sort of use that for the LED effect. The color doesn't matter. So even though the requirements, I think I said red and green or something, some of you may have gotten yellow strips or green strips or blue strips. So as long as it's two different colors in front and behind, then it's fine. Okay, so just use two different colors for the front and for the back. So if you have some other LED strip color, it's also fine. Okay, no issues about that. All right, so yeah, so that's all I have for today. The code-wise for the serial interface we'll go through next week, and then we'll also start the RTOS proper. All right, so this week what you can do is, like I said, this week and next week the lab is free. So if you have time, go and try to assemble up your robot, get your motor drivers up and running. Okay, if you are adventurous, okay, instead of using the breadboard, you want to do some prototyping with soldering and wire wrapping on small prototyping boards, also no problem. Okay, we can arrange for that, just let me know. Okay, but it's not necessary. Okay, so it is not that you do all this additional hardware, you get extra bonus marks. No, it is up to you whether you want to do it, you want to make your robot look more fancy, look more professional. It's up to you. All right. If you just want to do breadboarding, it's also fine. Okay. So if you want to explore other hardware prototyping, you just let me know. We will arrange for you. All right. But if you are happy with what you have, you just want to stick with that, it's also fine. All right. So this week and next week, try to fix up your robot, get everything up in terms of the motor and the drivers. All right. And next week, we will also integrate the regulator chip, the BTO6 module, and your app inside. So please also explore that part of it, creating the app, getting some basic functionality up. All right. And then I will go through with you next week how to put everything together and get the whole thing running. Okay. So once again, thank you very much. If any questions, you can stay back and ask me. If not, I will see you all next week or in the lab.
Prof, can I ask a question?
Yeah.
Prof, I noticed that most of the code, right, they contain a lot of pre-made masks because of the header files that we use.
Yes.
Is there a list of like such values like available for us to see or something like that?
Actually, basically the mask, you just need to refer back to the header file, the MKL25Z header file. So maybe I'll just share that. If you go to that header file, basically all the masks are defined there. Right? If you, I mean the reason with this mask, basically you know that you are accessing the correct bit location and setting the correct value. Right? If you want to use your own mask or you want to directly write a value, is also fine. But since we already have these masks, it will be a bit easier to use them.
Oh, no, as in like because I would like to use the mask, but it's more of like there is so many, and the only way we found out about them is like through your lessons every week like that. But I'm just asking, like, is it because the what's that, the functionality sheet, right, in doesn't really, the user guide doesn't really give us any information of such
Correct. Because okay, these mask and these header files are specific to the software side of it. Correct. The data sheet is on the hardware side of it. So if we are having access to all these masks because we are using this particular Q development environment with their framework. All right. This same microcontroller, you can develop code for it using different development tools. Okay, so there is other types. There is MCU Express IDE. There is another one from NXP. So there are different development platforms actually for the same controller. And if you use them, maybe you have different type of masks, different type of header files.
I see.
So the software aspect will vary depending on which platform you use. But the hardware is consistent. So the data sheet is consistent. So even if you don't have any of these masks, you can still go ahead and program it using your own mask, using your own bit masking techniques.
I see. Okay. Thanks, Prof.
Okay.
Can I just add, if you set up an IDE like VS Code to work with the with your C files, and if you add the header file properly to your to like your C include path, then it will give you suggestions including all the masks that are defined in the header. So that's really useful.
Yeah, correct.
Oh yeah, Prof, can I ask, like, if we create our own customized library, then inside the library we include the mkl.h file. Do you still need to, like, does it cause any problem with double include libraries? Like, let's say in the main function we include the customer library and the mkl library again.
Okay. what you can do is you can include it should be fine. It should be fine to include it again.
Okay.
Yeah.
Yeah, that's it. Thanks.
Prof.
Yeah.
Just now at the start of the lecture, you went through that one question, right?
Yeah. Yeah.
Can you explain again why you append zeros at the back?
Okay. Wait. Okay. So basically, you can see that we are configuring port D, correct?
Yeah.
So port D is tied to IRQ31. That is already fixed in the vector table.
Okay.
Okay, so that means for IRQ31, you can see down here that is in IPR7 register. Okay, IPR7 register, the upper two bits. So basically each IPR register is divided into 4 8-bit blocks. Okay, for 4 different IRQ. But for these 4 different IRQ, we only are configuring upper 2 bits of each of these 8-bit blocks.
Okay.
That means for IRQ31, which is here, okay, it is the upper 2 bits of the entire 32-bit.
Okay.
And I want to set it to a priority of 1. And priority of 1 means 0, 1. That means the value of 0, 1 will come here.
Okay. Then what happens if, let's say, instead of setting to IRQ31, we are setting to IRQ28?
Yeah, so the 0, 1 will come here.
Okay.
Or whatever value will come here.
Okay. Then the value will be
0, 0, 0, 0, 0, 0, 4, 0.
Okay, can. Yeah, understood. Okay, thanks.
Okay.